Time for a pop quiz.
Good morning, everyone. My name is Pen Center, and we are here this morning for, I believe it's number 6, Real Analysis Reading Group number 6, which I'm pretty stoked about. We have Horsey in today talking a little bit about derivatives. We're just waiting for the ads to roll through so we don't get interrupted. Or at least those of you coming on in a little bit later do not get interrupted by those pesky ads. So give us just a couple minutes here, and we will get the party started. Not 500. It feels like it should be an even number though. 8 times 8 is 64, right? Plus 6, so yeah, it should have an even. There's going to be an 80, there's going to be a... Oh, no, you're going to pick up some other stuff. There's like an 8 times... Oh, there it is.
Easy as pie.
Just a little bit shy. It's nice not to have Zach here, right? You can actually think about stuff when Zach's not here trying to steal those QED points. Let there be analysis, there will be analysis. You're almost there, about 25 seconds left.
I'm Mr. Meeseeks! Look at me!
All right, sweet. Let's pop back in the Discord and get this show on the road. Hello, everyone. Welcome on in. My name is Pen Center, and we are joined today with the one and only Horsey135. This is number 6 of our Real Analysis presentation. And Horsey's going to be talking a little bit about the derivative and maybe some properties of the derivative. So without further ado, I'll pass the floor over to you, Horsey, and you are welcome to get this party started.
Okay. Hello. Okay. Everyone can see the presentation? Okay. I hope it means yes. So, until now, when we spoke about functions, we usually spoke about continuous functions, and because they have a lot more rules to them and stuff that you can do with them. But if we will shorten our view to even smaller group of functions, to differentiable functions, we could learn quite a lot. So this is a definition.
Come on, Jeffrey, you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
2 points, and it is the slope between them as 1 point. It's closer and closer to the other. until when they get infinitely close, it becomes the tangent line to the function, and the slope of the function at this particular point. There are a few other ways to define a derivative. So this is also a very good way to define it, which I will be using. There's also a Leibniz way to write it, which is this df over dx. I don't like this, so I will not be really using it, but it is very important. Now, one thing is like, how do we take a derivative of a function? So first we can write the limit of the function, and if we will plug in the numbers, we can get this, and by expand it to this, and now we can remove most of those terms to get our goal, which is 2x. And this is actually a rule that we will see, that we can just put this number over here when we take a derivative of functions like this. Now, common usage of derivatives is to find minimum and maximum points relative. Usually, for example, if we have a function like this and we will take its derivative, quite big, but we can work a little bit around it and make it smaller.
Come on, Jeffrey, you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
We can find it, which yet again, like the function before, we can take the power of the x and put it before it. So this is a very nice rule. I think it's power rule, but I'm not sure. Now we need to find when it is equal to 0, because if we will have some function, for example, we can see that the tangent line at the minimum and maximum points is parallel to the x, and its slope is 0. At this point, if we'll take a little nudge to the right or a little nudge to the left, it doesn't matter, we will still be at pretty much the same number. And if we will take it, we can get these 2 points, which we can see that they are actually our minimum and maximum points of the said function. Now, there is a little bit more that we need to do, because not every time that we get in here a 0, it means that the function has a minimum or maximum at this point. A very good example for this would be the function of x cubed, which looks something like this. And at the point here at 0, its derivative is actually 0 if we will take it, but it does not have a minimum or a maximum point at here. But every function that has a minimum or a maximum point and it is differentiable at this point, the derivative is 0, which we will see later. Now, there are a few important derivatives. This is one of them with the x to the n, which we will see that if we'll take the derivative of it, now we can use the rule how to open this like this. No idea what's the name. And if you will just divide by both of these, we can see that this is what we get, and we actually have n of them in here, which we can see as we start with c to the 0 and end up in c to the n minus 1. So we actually have in here n of those. You can see which later is this, which this is the power rule. It's a very good thing when we take derivatives. This is a very common function type of this, x to the n. There's also the constant function, which is just c, which we can actually look if we have a constant function, when we'll go a little bit to the right or a little bit to the left, the value doesn't change actually. And it's so if we look at the Leibniz definition as the difference in f over the difference in x, we know that the difference actually in the y, the difference in the function is just 0. So this will just be 0. And if you will go on and open it, we can see that this is actually what we are getting. So we end up with this and this as two important derivatives for now. Now, we know that every function which is differentiable at c is actually continuous at c, which we can prove by taking this limit, and if we'll actually multiply and divide both by x minus c, we can see that this is actually the derivative, and we know that it is differentiable at c. So in order to actually just have the derivative of it times this, and this, if we will plug in c, is just 0, which means this is 0. And if this limit over here equals to 0, it actually means that the limit of f of x as x of c is f of c, which means it is continuous. But after we show that if it is differentiable, it is continuous, the question is, if it is continuous, is it differentiable? And the answer is no. And a very good example of it is the absolute value of x. If you look at its graph, it looks just like a V in here. You can actually see that if we will go, its slope and rate of change changes dramatically at the point 0. And so if we will take the derivative of it, we can see that it is the absolute value of x over x, which is not defined, because if we will take it from the right side, we'll get 1, but from the left side, it is -1. So we have a problem in here, so the limit is undefined, so it is not defined. Now is the sum rule of two functions. If we have two functions, f of x and g of x, so is and the f and g are differentiable. Is their sum also differentiable? And if so, what is it? So it is differentiable, because we can see that if we will take it, we can actually in here just take both of these and both of these and split them, and both of them are just the derivative of f and g at c. So we ended up that this is the derivative of their sum, which we will be using later. Now, if we have the sum, another question is, what is their product? Will they act like we expect them? Because we know that numbers, we have addition, multiplication, division, and subtraction. So is it also true with derivatives? Now we know that subtraction and multiplication and addition is the same thing if we just take the negative function, like negative f of x instead of plus f of x. So for the product, we can first write the limit, and now we will end up with this. Now this is a little bit more complicated, because in the end we want to have to pull out some f of x minus f of c and g of x minus g of c, which we can actually do by adding and subtracting this. So we know that if we'll take f of x out in here and g of c out in here, we get this. So we end up with this, which is not like a regular product or a multiplication of two numbers, but it is also very nice and a useful rule. Now with this, we can actually go and prove that if we will just multiply some function by constant, it will not affect its derivative and will just stay in there, because we know the derivative of a constant is 0. Now, division or a quotient, I'm pretty sure this is how you write it, or quotient, I'm not sure what. So what is it? Now this is a little harder, so we can actually split it into two derivatives. So the first one will be of 1 over g of x, which if we will take and then multiply like in a cross like this, we can get g of c minus g of x over x minus c. And this is just the derivative of a function, but the opposite, because the minus, though they are flipped. So we end up getting this. And with this, now that we have our product, if we'll take now the derivative of h of x times f of x, because we have the derivative of this and the derivative of this with the product of of derivatives, we can find it. So if we'll take it, we can split it like this. So we already know that this is the derivative of f of x times 1 over g of x plus the derivative of 1 over g of x times f of x. And if we will multiply f tag of x and divide it by g of x, we can do this because in here we have that g of x is different than 0. This is very important. Without this, we couldn't actually do a lot of the stuff that we're doing in here. And now with this, it's just a subtraction, and we end up with this, which is a formula that I'm sure most of you know. Now there is the chain rule. Now the chain rule is a little bit more complicated because we can't just go at it, but if we will try to just find it, we can see that in here we can multiply and divide by g of x minus g of a, and we can see that both of these look very much like derivatives, and in fact they are, and we get to this, but we have a problem, a very big problem, because we can't actually go from here to here because we don't know if g of x minus g of a is actually different than 0. And if it is not different than 0, then what can we do? Now, the thing that if it is, let's say, equal to 0, we know that it is actually at this very close proximity of a constant function. So we know that g tag of a should be 0, and all of it just should be 0, as we can see that if g of x is actually equal to g of a, all of this will also be 0. But proving it and saying it, we can just say stuff like this, but we can use a trick. So if we will define capital F like this, then we can see that as x approaches to a, g of x minus g of a approaches 0 or even gets to 0, and as this approaches 0, it approaches f tag of g of a. Now we are counting on this, that it is continuous actually at where g of x equals to g of a, but I will not prove it here. It is not that difficult, and it is actually a pretty nice exercise. So we can use it, and this will be very important. That as x goes towards a, capital F of x goes toward f prime of g of a. Now we can say that if we will take just this, it is actually equals to f of x times x minus a. And it again, notice that if g of x actually is equals to g of a, both of this is 0 and this is 0, both of those stuff. So we know that this, the composition of f and g at a is the limit as x goes to a to this. But now we can just swap this into here, and we will get this. And now if we will split it, we can actually see that this is just the derivative g prime of a, the derivative of g at a. And we know that this limit from the page before, we know that this is f prime at g of a. So we get to this, and this is pretty nice. Now we can use it to look at functions, for example, like this, that before we might needed to completely open it, which is annoying, or use some extra tricks. But now with this rule, we can actually split it into two functions. The first function would be x to the power of 5, and the second one would be x to the power of 3 minus 2x plus 4. And we can see that f of x equal g evaluated at h of x, which is pretty nice. Now we can find the derivative of g of x, which by the power rule that we proved earlier, we know that this is this. And here we actually need to use not just the power rule to move it to here, but we also need to use the sum of two derivatives to get to this. So now that we know that this is the derivative with the chain rule, we can just evaluate g prime of x at h of x. So we get this and multiply it by h prime of this of x, which is this. And this is a very nice way. Also, if we will go back to one of our first functions, we can actually look at this function that we looked at it before. Now, with the sum rule and the power rule, we can actually compute it much easily, because now we know that we can just put in here the 3 and remove 1, here the 2 and remove 1, and just delete the 6, and we get this, which is the same function that we got last time. Now there is another important derivative, which is e to the x. Now e, Euler's number, is actually defined in some ways to be the number such that a to the x, if we'll take its derivative, will just be a to the x. This is one of its main properties, and a pretty cool property. Now, to evaluate this, we are going to need to use a limit, which is this limit. I will not go over this limit. We'll just take it as a God-given limit for now. Now, I will actually prefer to use it with an h, because in here I see that we're using h going to approaches 0, and in here we have n approaches infinity, so it will be nicer instead of x to a to have h to 0, because we can easily just make it to a 1 over h or something and get approaches to infinity like you want to. Now, if we'll open it, we can see that e to the x appears both in both of these, so we can just factor it out, and we need this. Now, because h doesn't appear in e to the x, we can take it out. So now all we need is to find this limit. Now we're going to use this and define n to be e to the h minus 1. Now we can see that as h goes to 0 or as n goes to 0, they affect the other one as well. So if we'll open it, we can get that e to the h equals n plus 1. If we'll take the natural logarithm of both, h equals ln of 1 plus n. Now we can actually plug both of those in here, and we will be very close to finding the derivative. Now, when we plug it, we get this limit. Now, this limit is not good enough for us because we already see the 1 plus n as n goes to 0, which is the same thing as n goes to infinity and 1 over n. So all we need is this in here. Now, if we'll actually multiply both sides by 1 over n, we can get this limit, and with logarithm rules, we can put the 1 over n in here. Now we know that we can split the limit. So all we need is to actually find this limit right here as n approaches to 0. But we can actually swap it with the 1 over n and goes to infinity. So we get 1 over the natural logarithm of e, which is 1. So we just have 1. Because we have 1 and we know that the derivative is e to the x times this derivative, and this derivative is 1, we actually know that the derivative is e to the x, which is pretty nice, as this is the function that it is its own derivative. So if we'll continue to take more and more and more and more derivatives, it will stay the same. Now there is another function, which is the natural logarithm. This natural logarithm. Now we need to compute this derivative. We can actually use pretty much the same thing as we used in here to prove it, and it is a pretty fun thing to do, as it is basically the same thing, just with the ln at the start. So this is actually what we have for the ln of f of x, which is f tag of x over f of x. Also, if, for example, we have just random a to the x, if we'll make it into e to the ln of a times x, we can actually take its derivative and get, which is ln of a times e to the ln of a times x, which is just a times a to the x. So this is the derivative of this function, but usually you start it with e to the x, or just want to keep it as e to the x because it is a very nice number by Euler. Now, from the start, when we used the derivative to find the maximum and minimum point of a function, which looked like this, and took the derivative, we actually counted on this theorem that if some function has a relative minimum maximum at x and it is differentiable at x, then the derivative is 0. Now, the proof is not this hard. I will show the minimum case, but the minimum and the maximum cases close enough that just this will be enough. Yet again, I will use as h goes to 0, because now I can say that because it has a minimum, then it is smaller or equal than all of the others, right? This is how we would define it, as smaller or equal to all of the other points in some close proximity of it. So if you would just put in here, we get that this is greater or equal to 0. And because we're taking the derivative from the right, we know that h will also be positive. And if we'll take from the left, we'd get the same thing, but this time h would be negative. So we know that this function is to be greater or equal than 0 and smaller or equal to 0, which means it needs to be 0. This is a very useful theorem, as one of the main usages of derivatives is to find minimum and maximum points in all sorts of functions. But with this, we can actually prove another theorem, which is pretty cool, which is the Darboux theorem. So the idea of it is that if you will have some function a and b, we know that every point between f of a and f of b, because it is continuous, differentiable to continuous, we know that it has every value between f of a and f of b in this area. But we can say an even stronger thing, that it has every value between the derivative of the function has also the same property, that it has every value between f prime of a and f prime of b. So the function has every value between this and this, and the derivative also have it. Now we can actually split it into a few cases. So the first one is if t is equal to f prime of a or f prime of b. Second one is if t is between them like this, or t is between them like this. Both of these cases are almost identical. So we actually know this one, it just x is a or b, which is the simplest one of them. So let's prove it. Now we can define a function like this. And the idea is that we can take the derivative of the function and be left with the derivative minus t. So we just added tx. So because we know that it is differentiable, so continuous, at a closed interval, we know that it has a minimum, a relative, like a minimum at a b with this, the extreme value theorem. Now, because it has a minimum, we know that if we'll take the derivative at a, we know that f prime of a, now in this case, right here, f prime of a is smaller than t, so f prime of a minus t is smaller than 0. But we also know that if it had a minimum at a, we know that if it had a minimum, and we will take it from the right, we know that g of x minus g of a g of x minus g of a is larger or equal to 0, and we know that x is larger than a because we take it from the right. So we know that it is larger than 0, but we have a conflict larger than 0 and smaller than 0, so we know that g does not have a maximum at point A. And if we will do the same thing, but at B, we know that B is larger. 1 second. Now that it is larger than 0, so if it will have a minimum, this time because we're coming here from the left, we know that it has to be smaller or equal to 0, which yet again doesn't stand well with this, that it has to be larger than 0, so it doesn't have a minimum at this point either. Now, because we know that we have some function when this is a and this is b, and we know that it doesn't have a minimum at a or at b, then it has to have a relative minimum somewhere in here. So it has to have a relative minimum in here. And the relative minimum, because of Fermat, we know that if it is differentiable and the relative minimum, then it has to equal to 0. So with this, we can say that it has some point which it has a relative minimum of at it. So because of the Fermat theorem, we know that g prime at x is 0. And by the way we define g prime, we know that it means that f prime at x minus t equals 0. So f prime of x equals to t. So we have some value in here. This is also pretty nice. There are a few variations to it and a few different ways to define it. And there is also that this function somewhere in here has the slope between a and b. So if this is the slope, some point in here, the derivative, the tangent line is this slope. This is also something that you can prove, but I will not go over it now. Now, it's actually another pretty nice usage of derivatives, because until now, we actually used limits to define derivatives, but we can also use derivatives to find limits. Now, this is a very powerful tool to find a lot of derivatives, and this is L'Hopital's rule, which actually L'Hopital did not find. He just bought it from Bernoulli with money. He bought the rights to this rule, so he didn't prove it actually. So this is L'Hopital rules, but the idea is that if we have some two functions and we take their limit, and both of them are, for example, 0, and we get that it is 0 divided by 0. Now we don't know actually how to compute it, 0 divided by 0. So we can just find the derivative of both of them. The limit should still be here. And we can actually continue to do this again and again and again and again, as long both of them are 0 divided by 0 or some variation of infinity. Now, I will not prove it, or be something I forgot. We'll prove it next week, I think. But we can actually use an example in here. For example, this function, if we'll actually try and plug in 2 in here, we can see that this is 0, and this is the natural logarithm of 1, which is 0. So we end up having 0 divided by 0, which is not good. So now we also know that both of these functions are differentiable at the closed interval 2. So we can take the derivative of the top function divided by the derivative of the small function. I think I flipped it, yeah. It should be like this. I organized it wrong. But we can use it. Now, something that we should notice, that when we take the derivative, we take it as f prime of x divided by g prime of x, and not the derivative of f of x divided by g of x, because by what we proved earlier, it is different than what we want, and this is not good. This is something to notice and make sure that you don't fall on. But now we can actually plug 2 and get a reasonable function, which is 81 divided by 4. Now, this is an example, but the main idea of it is to help find some very advanced limits. And a famous one and a weird one is this: sin of x over x. Now, the problem with this, that when we use the derivative of sin of x to define it as cosinus of x over 1, we're actually using the derivative of sin of x, which is usually found with this limit being 1. So it is problematic because to find sin of x, the most famous proof usually revolves around this limit being 1. And the easiest way to prove that this is 1, of course, is just by taking the derivative of it. And we can just get to 1 pretty easily. Now, with L'Hopital's rule, we can actually jump through a lot of stuff and not use epsilon and gamma. I think this is how you write gamma. To find limits and use L'Hopital's rule. L'Hopital's rule actually have a few more variations, quite a lot. There's also variation as the limit as x goes to infinity, not just as x goes towards some number, some constant number. But to sum up, mostly what I went in here is that derivatives have their own rules about addition, multiplication, division, composition, and so on. But the easiest way to actually improve with derivatives is to do a lot of them. There are a few really easy ways to check if you're correct with stuff like Desmos Wolfram alpha. Which both are pretty nice, and you can easily check if you're correct. Yeah, the main idea is to find functions that you see them as interesting and to try and take their derivative. Also, a cool thing is multivariable calculus. I will not go into details, but it is very fun and interesting. Yes. So this is mostly what I have to say about derivatives. Just practice a lot, and don't afraid to make them blow up into some very large, especially in this type of derivatives. It gets very big, very fast, especially when we just put it into some random stuff like e to the power of it, this to the power of something, and so on. Yeah, I don't have much more to say. I know it was a little short, this presentation, but yes, this is what I have.
Oh, amazing. Thank you so much for coming in and chatting a little bit about derivative rules today. I'm going to open up the floor, so if there are some questions either on Twitch or in Discord chat, feel free to post that up here for Horsey and I to talk about. There was a little bit of discussion about one of the proofs that you did. Which one was it? It was for the limit as I think it was like e to the h minus 1 over h, right? That limit tends towards 1. And
Yes.
you use that really nice fact that provided you have a continuous function, you can kind of move the limit into that logarithm. And so there was a little bit of discussion about that in Discord chat. Just in case you're curious, it's just it was AL that was talking about that with me, and it's a consequence of something we talked about last week, which is the sequential criterion for limits. So if you're kind of curious about how that works, I posted a little bit of information in Discord chat for you.
Yeah, I'm reading.
Yeah, and AL says the L'Hopital's rule's power becomes more emphasized when we're dealing with limits involving integrals. Yeah, because there's that really nice fundamental theorem of calculus aspect you can use there.
But integral is not for now.
But yeah, we'll be taking a little bit of a break after we get through the derivative part of kind of our introduction to real analysis. But I am hoping to kind of come back a little bit later after I'm finished my semester, maybe during the summer, and kind of pick up and talk a little bit more about Riemann integration, which is kind of the final part of the Abbott book. So hopefully we'll be able to come back and do that too. Go ahead, Horsey.
I'm waiting for derivatives. Actually, I'm actually not very good at integrals. I am like I am working on my skills with them right now.
They can be a little tricky, right? Like they're quite challenging, and a lot of the techniques that we learn in our like calculus classes are pretty tough.
Yeah. Also, 3 Blue 1 Brown has a great series about calculus.
Yeah,
which
3
is
Blue 1
pretty
Brown
nice.
has some great series on a lot of mathematics.
Yeah, I know.
Worthwhile checking that out for those of you that are watching.
Yeah.
All right. I haven't seen any kind of major questions or concerns coming in, Horsey, so thank you again for a little discussion on derivatives. So for those of you who are interested, we're going to post this up to YouTube. We'll get some of the, Horsey, if you're okay to maybe pass the slide deck over to me, we'll post those resources for everybody.
Yeah, I can send you the slide.
Amazing. Yeah, and for those of you that aren't in the category for real analysis, just shoot me a message on Discord and I can get you the role that you need to get into that category. Also, I want to take a moment to just do a little shameless plug. We have Zyphon in Twitch chat right now. I know Zyphon and Slender have been working on getting a topology reading group started in the Mandelbrot mathematics server as well. And their first presentation is going to be tomorrow. It's going to be 9 o'clock a.m. my time. But I'm going to go ahead and add that to, I think I've added it as an event, actually. So if you're curious about that, you can check out the event over in the Mandelbrot Math server. And hopefully Zyphon will put like a little announcement out to everyone so we can get updated all over our servers. So thanks again, Horsey. Have a fantastic rest of your day.
Yeah,
I'm going to go ahead and start to shut down.
Okay, wait. So, well, like in Discord, send you the presentation, or Don't you want over email? Like,
Are you able to like send it in a? You can either send it in a DM or you can post it in the presenters channel if that works for you.
okay. I will post it in the presenter chat right now.
Perfect.
Okay.
All right, everyone. Take care. Have a fantastic rest of your Saturday. It looks like Zach just popped online, so we're going to go ahead. We're going to raid over into Zach as I shut everything down over on the Twitch side and Discord side. So let's go ahead and say hello to Zach. Give me a second to get the bot back up. But hopefully you guys had a fantastic time learning about derivatives. And when are we back? Well, obviously we have our topology presentation tomorrow morning. We'll also be back tomorrow morning with Stuckey. We're trying to finish up a little bit of the Friedberg linear algebra reading group. So we're going to be kind of working away at that tomorrow morning as well. Let's get some tunes in here. And then Zach and I are going to be back on Monday and Wednesday this week. I have 2 more classes before we take a little bit of a break from our exploratory linear algebra. So we'll be back in the morning on Monday and Wednesday as well. So lots of stuff happening. Tomorrow we got topology, we got linear algebra, we got Talos doing calculus tomorrow evening, and then linear algebra again on Monday and Wednesday this week. We'll be back hopefully with OB next week for our kind of final real analysis before our break. So hopefully we'll see you all in chat. You're very welcome, Zyphon. Thanks for coming and hanging out for a little bit. Like I said, we'll go ahead and raid over into Zach. If you need a raid message, feel free to grab one of those raid messages as we hop over into Zach's channel. Thank you very much for the follows today, 1010. Oh, we got a Aspire as well. Thank you very much for the follow, guys. All right, take care, guys. I'll see you tomorrow morning. Hopefully we learn what is an open set in topology. Ooh, I don't know. Maybe we'll learn about that. Maybe. Maybe. Isn't that the whole point of topology? Open sets get mapped to open sets. Oh, Drew. You know how to make me smile on a Saturday morning. All right, bye, everyone. Take care.